Imagine reading a text where all the spaces have vanished and the letters themselves have merged and transformed according to complex phonological rules. This is the daily reality of Sanskrit, where over 281 sandhi rules obscure word boundaries, turning what should be distinct words into seamless phonetic streams. Today, we'll explore how modern computational methods are solving this ancient puzzle. Let's first understand what makes this problem so remarkably difficult. Building on that challenge, Sanskrit presents three compounding obstacles. First, sandhi physically transforms the text, inserting, deleting, or fusing phonemes so boundaries become invisible. Second, the space of possibilities explodes. One string can generate 625 candidate splits. Third, validity requires more than phonetics. Context determines which segmentation actually makes sense. The traditional solution uses finite-state transducers, paired with morphological lexicons. These systems generate all phonetically plausible splits, check each chunk against a dictionary, then rank candidates by corpus frequency. While interpretable and achieving reasonable coverage, they struggle with out-of-vocabulary words and genre variation. Neural models transform this landscape by learning segmentation patterns directly from data. Contrasting the two paradigms reveals complementary strengths. Rule-based systems offer transparency and strong top-K recall, but falter on novelty. Neural encoder-decoder models, treating segmentation as sequence transduction, generalize better and push token level F1 past 90%, though at the cost of interpretability. Translis represents the state-of-the-art by marrying transformers with linguistic structure. It uses soft masked attention to guide the model towards spans suggested by classical tools, then ranks all valid paths through that lattice. This architecture gained over 7 percentage points in perfect match accuracy, proving that neural power plus linguistic inductive bias beats either alone. Meanwhile, byte-level transformers like ByteE5 Sanskrit take a radically simple approach. Train on character sequences end-to-end. No handcrafted features. They achieve comparable or superior perfect match rates, and when augmented with lexicon-generated candidate prefixes, rival even Translist. This demonstrates that sufficient model capacity and data can internalize the sandhi logic. Despite impressive progress, hard problems persist. True ambiguity means even human annotators disagree on certain splits. Long compounds with nested sandhi, rare archaic forms, and the jump to related but under-resourced languages all present open research questions. Future systems will likely blend neural learning, linguistic constraints, and semantic reasoning. This research isn't confined to the lab. Modern segmenters underpin every serious Sanskrit NLP application, from parsing ancient manuscripts to building multilingual lexicons for Indian languages. Open-source tools and REST APIs now let researchers, educators, and heritage institutions segment text at scale, democratizing access to classical knowledge. Sanskrit Word Segmentation beautifully illustrates how computational linguistics can honor and extend millennia-old grammatical tradition, achieving over 93% accuracy by fusing transformer architectures with linguistic insight. To explore more breakthroughs at the intersection of language, culture, and AI, visit emergentmind.com.